Hello, everybody. Today we'll speak about Gaussian quadrature again, and we will solve the third exercise of this category, which is the integral that you see here. So this double integral, which is seen here in the picture, which is defined in the interval -1 to 1 for x and -1 to 1 for the y variable. For this reason, no transformation is needed since both of our variables have the default values. We have the default intervals -1 to 1. This is our function. We have two variables, and here you can see a plot of this function where x here is from -1 to 1, and again y is from -1 to 1, and this is the surface that describes our function. Our aim now is to find the area below this graph, below this surface, which is the integral, the double integral of this function in this interval -1 to 1 for x and y. Things are simple since we have no transformation to make, and we will try 3 times using 1, 2, and 3 Gauss points in each direction. We start with one Gauss point, which is the simplest solution, but also it is not so accurate. Here you see the table from the theory, which describes the Gauss points exactly and the weights that we need to take in each case. For one Gauss point here, we see that we have to use the 0 point. So my point will be the 0, 0 point. 0 for x and 0 for y. And in this case, the weight is 2. So my first approximation is only given by finding the value of f at 0, 0, and then multiply this value with the weight, which is 2. So I can easily find that f of 0, 0, it is x and y 0, so the value is 1. So my first approximation I is 2, which is the weight in one direction times 2, which is the weight in the other direction times 1, which means that this integral, the approximation is 4. So using one Gauss point, I end up to the value of 4 for my integral as an approximation, but as you see here, the accurate solution is in fact 8. So I can see that this approximation using only one Gauss point is not so good. In this case, I used, let's say, this is the domain. So in this case, I used only the 0, 0 point as one point for my approximation. Second, we will do the same using now 2 points per direction, which means 4 Gauss points in general. Now we have this picture where again we have the interval. We have the region here, -1 to 1 for x, -1 to 1 for y. And now we go to the table and you will see that with 2 points, these are the values of the points and the weight is 1 in each case. So instead of using the 0, 0 point, now I have to use some other points that can be defined here. 1, 2, 3, 4. So this here, let's say, is the first point, second, third, and fourth. One here, 2, 3, and 4. These are the 4 points that I will use now for my approximation. For example, point 1 lies at -1 over square root of 3 for x and -1 over square root of 3 for y. Point 2 lies at -1 over square root of 3 for x and then +1 over square root of 3 for y. And similarly, point 3 is at 1 over square root of 3 for x and then -1 over square root of 3 for y. And for point 4, both are positive, 1 over square root of 3 and 1 over square root of 3. So these are my points now. And let's see the weights. The weights are 1 for each point. So, and using two variables, I have to multiply the weights. So in every case, it is 1 times 1, which is again 1. So it is rather easy to calculate again the values of the function and then multiply to find the integral. I can remove this picture as I no longer need it, and then I can now make a table which will be 1, 2, 3, 4, my 4 points, and then I will write the x and y variables. So in this case, the first one is this one, which is -1 over square root of 3, and the y is again the same. And easily, I can also write the other ones, minus, minus, and then plus. And the y values are again plus, minus, and again plus. So these are the x and y values of my points. Then I have wx and wy. All of them are 1 in this case, because according to the theory, with two Gauss points, the weights are 1. And then all I need to do is calculate the value of f at these points. And then the value of wx, wy, and f, applying the weights, which is, in my case, this will be exactly the same before, because the weights are 1. So if I calculate the value of the function, I will find the following. These calculations can be easily done in Excel, but you can do it also by hand. And in my case, Wx, Wy, F is again the same. So I can simply write the same values again. And all I need now is to add these values to make the sum, to take the sum. And if I do it, I will find that this sum is 6.2222. So this is now my estimation for this double integral using this time 2 Gauss points per direction. And again, we see that the estimation is not so good because the accurate value is 8 and we found 6.22. Now we can give it a try using 3 Gauss points per direction. So we move on, and now we will use 3 Gauss points per direction, which is using this, and we have these 3 values for x, and these 3 values here for the weight. 8/9 for the 2 points, the minus and the plus, and 5/9 for the middle point in the center. Let's go to see this case now. For this case, we have 3 Gauss points per direction. Let's write a 3 here. And again, I will make my region, which is this one. These are the axes. And now I have 3 points per direction, which means that I will use a central point, and then I will use also points on the left and points on the right. And I will have 9 points in general, as you see here. 3 points each direction, 9 points in general, including the 0, 0 point in the center of the element. And I can also write my points as 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9. So these are my 9 points that I will work with, and I will use these weights here for these points. I need to make another table for this case, so I will do it right now, where again I need to write 9 points. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I need the x variable, which in this case, it is minus 0.77460. And then the y point is minus 0.77460 again. This is x and y. And for x, I repeat the same number 3 times. The next x is 0. So I have 0, 0, 0. And the next x is plus 0.77460 with a plus. And the y, as you see, it is 1, 2, 3 here. So I can say that it is minus and then 0 and then plus. So again, I have the zeros here, minus 0 plus, minus 0 plus, and I can write the numbers as you see here. And then again, minus. I have my x and my y values, and now I need the wx and wy values, which are the weights that I will use. So if you go here, you will see that the outside points use 8/9, and the middle point, excuse me, the middle point uses 8/9, as you see here. And the other points use 5/9. So I will combine these two. Wherever I have 0, it is 8/9 for x. And for the other, it is 5/9 for all the others. The same for y. Wherever I have 0, it is now 8/9. And wherever I have not 0, the other points, it is 5/9. I'm almost ready. I now need the value of the function f at the point xy. So you can easily calculate the value of this function. Excel is good for this. If you use a calculator, it will take you some time, but Excel is fine. So I will quickly write the values of this function, if you calculate them properly. So this one is it. One and 7.3384. Having the values of the function, I can now easily do the multiplication f xy times wx times wy. So I multiply these three values to get the last column for this exercise, and I will simply write the values that you will get if you do this multiplication. So this is now what we will do. And after you do this, then last, you need to add all these values together, a big plus here. And if you do it, you get the sum, which is exactly 8. So by using 3 Gauss points per direction, 9 Gauss points in total, we managed to approximate exactly, to find an exact solution for this problem, which is described here. And then we have a success. So for this problem, we needed these 9 Gauss points, 3 per direction, to find a good and accurate solution. Thank you for joining.